Bismillahirrahmanirrahim. Dear students, Assalamu alaikum and welcome to the course of Mathematical Methods of Physics 2 having course code PHY 222. I am Dr. Abdullah Yar, Associate Professor in the Department of Physics, Kohat University of Science and Technology. It is my ninth lecture about the second solution of second order linear homogeneous ordinary differential equation. The primary objective of this lecture is to enable students evaluate the second solution of second order linear homogeneous ordinary differential equation, which cannot be evaluated by using the series substitution method. This lecture consists of two parts. In the first part, we will discuss the linear independence of solutions with a couple of examples, whereas in the second part, we will evaluate the second solution of a second order linear homogeneous ordinary differential equation, followed by a few examples. From linear algebra, we know that two vectors a and b are said to be linearly dependent if there exist non-zero constants k1 and k2, such that if you multiply k1 a by k1 and vector b by k2, if their sum is equal to 0, then the vectors a and b are linearly dependent. Otherwise, if this sum is not equal to 0, then the vectors a and b are linearly independent. Now let us consider differentiable functions f of x and g of x as being vectors in the vector space of differentiable functions. Then they are called linearly dependent if there exist non-zero constants k1 and k2, such that if you multiply the function f of x by k1 and the function g of x by k2, if their sum is equal to 0, then the functions f of x and g of x are linearly dependent. Otherwise, if this sum is not equal to 0, then the functions f of x and g of x are linearly dependent. It means that for a given set of functions phi mu, the criterion for linear dependence is the existence of a relation in the form sum over mu k mu phi mu equal to 0, in which not all the coefficients k mu are 0. However, if the only solution of equation number 3 is k mu equal to 0 for all mu, then the set of functions phi mu is said to be linearly independent. Now let us assume that the functions phi mu are differentiable. Then we can generate a set of equations sum over k mu phi mu prime equal to 0, k mu sum over mu k mu phi mu double prime equal to 0, and so on. This yields a set of homogeneous linear equations in which k mu are the unknown quantities. So there exists a solution k mu not equal to 0 only if the determinant of the coefficients of the k mu's vanishes. Hence, restricted the discussion for mu equal to 2. For simplicity, we have the phi 1, phi 2, phi 1 prime, phi 2 prime equal to 0, and this determinant is known as the Wronskian, which is denoted by w of x. Consequently, if w of x is not equal to 0, then equation 3 has no solution other than k1 equal to k2 equal to 0. Then the functions phi 1 and phi 2 are called linearly independent. However, if the Wronskian vanishes over the entire range of the variable, then the functions phi 1 and phi 2 are linearly dependent over this range of the variable. In summary, for any two functions phi 1 and phi 2, if their Wronskian is equal to 0, then the functions phi 1 and phi 2 are linearly dependent. However, if their Wronskian is not equal to 0, then the functions phi 1 and phi 2 are linearly independent. So this concept can be generalized for a set of n functions whose Wronskian is given by w of x equal to phi 1, phi 2, phi 3 up to phi n, and the second row consists of phi 1 prime, phi 2 prime, phi 3 prime up to phi n prime, and so on. For linearly dependence or independence, the aforementioned procedure can be adopted, meaning that if w of x is not equal to 0, then equation 3 has no solution other than k mu equal to 0, and in this case the set of functions phi mu is called linearly independent. However, if the Wronskian vanishes over the entire range of the variable, then the functions phi mu are linearly dependent over this range of the uh, variable. No, the linearly dependence or independence in terms of the Wronskian can be better understood by solving a few examples. Now, in example 1, we need to show that the solutions of linear harmonic oscillator are linearly independent. We know that the linear harmonic oscillator is described by the equation y double prime plus omega square y equal to 0, whose solutions are phi 1 of x is equal to sine omega x and phi 2 of x cos omega x, which can be obtained by using the Frobenius method. Now, the Wronskian of these functions is given by w of x equal to phi 1 phi 2 phi 1 prime phi 2 prime. Now, in this determinant, if we substitute the value of phi 1 and phi 2 from these equations and evaluate their corresponding first order derivatives, then we will obtain this expression for the Wronskian of the harmonic oscillator. Now, this determinant can be evaluated giving minus omega, which is not equal to 0, which shows that the functions phi 1 and phi 2 are linearly independent. In the second example, we need to show that whether the set of functions given by phi 1 of x equal to e power x, phi 2 of x equal to e power minus x, phi 3 of x equal to cos hyperbolic x are linearly dependent or they are linearly independent. To show this linearly dependence or independence, we need to evaluate their corresponding Wronskian, which is given by the determinant of the 3 by 3 matrix. Now, if we substitute the value of phi 1, phi 2 and phi 3 in this determinant and evaluate their corresponding first order and second order derivatives, then we obtain the relation for the determinant of these functions. Now, this determinant is 0 because the first row and the third row are identical, which shows that the functions e power x, e power minus x and cosine hyperbolic x are linearly dependent. Now, in the second part, we evaluate the second solution of a linear second order homogeneous ordinary differential equation, which in the general form can be described as y double prime plus p of xy prime plus q of xy equal to 0, where p of x and q of x are the coefficients of the differential equation. Now, let us assume that y1 and y2 are be two independent solutions of the equation number 10, then their corresponding Wronskian is given by w of x defined by y1 y2 y1 prime y2 prime and is equal to y1 y2 prime minus y1 prime y2. Now, equation number 11 can be differentiated with respect to x, leading to w prime equal to y1 prime y2 prime plus y1 y2 double prime minus y1 double prime y2 minus y1 prime y2 prime. In this equation, the first term and the last term can be cancelled, leading to y1 y2 double prime minus y1 double prime y2. Now, in the first term, we can substitute expression for y2 double prime from equation number 10, leading to y1 into minus p of x y2 prime minus q of x y2 minus for the second term y1 double prime can be again substituted from equation number 10, leading to minus 2 y2 minus p of x y1 prime minus q of x y1. Now, this term and this term will be cancelled out, leading to minus p of x into y1 y2 prime minus y1 prime y2. Now, the expression in the parentheses is the same as the right hand side of equation number 11. That way we obtain y prime equal to minus p of x w. Now this is first order homogeneous ordinary differential equation which can be solved by using the separation of variables, leading to dw divided by w equal to minus p of x dx. Now equation number 13 can be integrated over the variable x from a to x, yielding natural log of w of x divided by w of a, which is equal to minus integral from a to x p of x prime dx prime. Further simplification of this equation leads to w of x equal to w of a exponential minus integral from a to x p of x prime dx prime. Now equation number 11 can be expressed as w, which is equal to y1 y2 prime minus y1 prime y2 prime. This expression can also be described as y1 square d divided by dx y2 divided by y1. Now equation number 14 and 15 can be combined, leading to d divided by dx y2 divided by y1 equal to w of a exponential minus integral from a to x p of x prime dx prime whole divided by y1 square. Now equation number 16 can be integrated from x double prime equal to b to x double prime equal to a, which yields y2 of x equal to y1 of x y2 of b divided by y1 of b plus y1 of x w of a integral from b to x exponential minus integral from a to x double prime p of x double prime dx double prime dx prime whole divided by y1 square x double prime whole square dx double prime. In equation number 17, a and b are arbitrary constants, and the first term on the right hand side of equation number 17 can be dropped because it leads to nothing new. Since w of a, which is the Wronskian evaluated at x is equal to a, is a constant, and our solutions for the homogeneous differential equation always contain an unknown normalizing factor, that is why we can set w of a equal to 1, and consequently equation number 17 can be described as y2 of x equal to y1 of x integral over x exponential minus integral over x double prime p of x prime dx prime whole divided by y1 square x double prime whole square dx double prime. In equation number 18, we have omitted the lower limits at x prime equal to a and x double prime equal to b. Now the expression in equation 18 is the expression for the second solution of second order linear homogeneous ordinary differential equation. Now to better analyze the second solution, we need to solve one example. And in this example, we are given that one solution of linear harmonic oscillator equation oscillator is y1 of x equal to sine of x, and we need to evaluate the second solution. So the equation of linear oscillator having this solution can be described by y double prime plus y equal to 0 if we compare this equation with the general form of the second order linear homogeneous ordinary differential equation described by y double prime plus p of x y prime plus q of x y equal to 0. We obtain p of x equal to 0 and q of x equal to 1. Now if we substitute the value of p of x equal to 0 and y1 of x equal to sine x in equation number 18, which leads to y2 of x equal to sine of x integral over x 1 divided by sine square x double prime dx double prime. The simplification of this integral leads to minus cotangent of x. If we simplify this expression, we will obtain minus cosine of x. Hence the second linear independent solution of linear oscillator equation is y2 of x is equal to minus cosine of x, which can also be obtained by using the Frobenius method. With this, I end up my ninth lecture.